Okay guys, let's talk now about generative learning models. In this presentation I will explain the general generative model, how you create this kind of models, and then I will talk about how you can implement a Gaussian discriminant analysis model, which is a kind of generative model. And finally I will discuss some points related to decision theory, which are important when you implement classifiers. So, okay, consider a classification problem in which we want to distinguish between elephants, label 1, and dogs, label 0. And we are going to make this classification based on some features of the animal. Suppose that these features are, for example, the height of the animal and the length of the tail of the animal, for example. Given a training set, then using an algorithm such as logistic regression or perceptron, we would find a line that works as a decision boundary that separates elephants and dogs. So in the work we use discriminative functions. If our points are in a two-dimensional space, then we need to find a line to classify these points. If our points are in a three-dimensional space, we will need to find a plane. If you're working on a higher dimensional space, then you will need to estimate some hyperplane. Now, this is the approach with logistic regression using discriminative functions. With generative models, the approach is different to this. In generative models, we talk about probability distribution. So what we do is first we build a model. A model is a probability distribution of how elephants look like. Then we build another model, another probability function of how dogs look like. And finally, to classify a new animal, we simply need to compute the probability that the new animal belongs to the group of elephants. And we write down the probability for that model. Then we calculate the probability that that animal belongs to the other group, the dog. And we will have another probability. So then we simply check which one of these probabilities is the largest one. And then we can make a decision. So in this case, suppose that the label for dog is 0, the label for elephant is 1. Then we need to estimate this probability, this conditional probability distribution, which is the probability that an animal, which is a dog, will have certain features, certain height, for example, or certain length in its tail. And the same, we will need to compute or estimate the probability, the conditional probability for elephants. What are the probabilities that some elephant will have some height and some length in its tail? So the problem in these generative models then consists in estimating these probability distributions. Once we have done that, then we can apply the Bayes rule to make our classification. So suppose that you have a new animal with some features X, and you want to classify this animal, then you will need to compute the probability that that animal is a dog. So when probability of Y equals 0, given the current features of the animal, and you will compute it with this. And then you will need to evaluate what is the probability that Y equals 1, so that the animal is an elephant given the same features. And these two results, you just need to check them and see which one is the largest one to make a decision. This denominator here, if you remember, you can compute it simply by summing the product for each of the possibilities of the label. So in this case, we're talking only about two labels, 0 and 1. So we will have here the probability of X given Y equals 0 times the probability of Y equals 0, and plus the other option when we say that the Y is 1. So the probability of X given Y equals 1 times the probability of X equals 1. If we had, for example, one more category, one more animal, for example, then you would need to compute here plus the probability of x given y equals 2 times the probability of y equals 2, and so on. You can keep increasing the number of classes, but this is the very basic problem in which we have a binary classification problem. Now, once you have estimated these three probability distributions, then as we said, to classify a new animal, we need to evaluate the model of animal and the model of dog and assign the category based on the largest probability. So we basically have to do this. We have to compute this numerator here, this denominator, compute the number, and check which label has the largest value in this. So we want to find the maximum of this for every possible label, and the one that has the largest one, the argument y that makes this a maximum, then this is the class that we have decided, the most probable class. Now here in the numerator, for example, in the case of dog, you will compute the probability of x given y equals 0 times the probability of y equals 0 divided by the probability of x. Okay, when you go and then calculate the probability of being an elephant, then you will compute the probability of x given that y equals 1 times probability of y equals 1. Okay, so this numerator is going to be different when you change here the label, but if you notice, the denominator is going to be exactly the same when you compute this for dogs and for elephants. So in practical terms, if you want to compute this as fast as possible, you can basically delete the denominator and you can simply compute this product and check which of these products is largest, for y equals 0 or for y equals 1. Now if you do that, you just need to take into account that this number is not a probability anymore. To make it a probability, you would need to divide it by probability of x, so you can normalize it. If you compute only the product, this is just a number. You can take it as some score that will allow you to classify the animal, but it's not a probability anymore. Okay, so in general, this is the approach in generative models. You define the labels as probability variables, random variables, estimate conditional probabilities, and then you apply base rule to make a classification. Depending on what kind of distribution you decide to use, the method is going to be a different method. So a very important method in this family is the Gaussian discriminant analysis model. In Gaussian discriminant analysis, we assume that the examples behave as a normal distribution, as a Gaussian distribution. I have written here the formula for the probability of a Gaussian distribution when x is a vector of input variables or features, and here sigma is the covariance matrix, and mu will represent the mean vector. So it is important to review this, the elements in this formula, because this is the element that you will need for implementing Gaussian discriminant analysis. So let's see how we can do that. Suppose a classification problem in which the input features x are continuous valued random variables. If that is the case, then we can use this GDA model, the Gaussian discriminant analysis model. So important point here is that we are assuming that the input features are continuous valued, okay, like the height of the animal or the length of its tail. Okay, so In terms of y, the label, we will assume that this can be generated or drawn from a Bernoulli distribution with some probability pi given or known. And we will assume that the probability that x takes some value given that the label is 0 can be drawn from a normal distribution with some mean 0 and some covariance. Okay, if we were talking about x to be a scalar, then we will have here a mean number, a scalar also, not a vector, and we will have here the variance. But since we are talking about several features, like in this case 2 features, the height of the animal and the length of the tail, then we have a vector, and here we will need to compute a mean vector of the features, and this is, instead of the variance, we will then need to compute the covariance matrix, which is a square matrix. Okay, in the same way we will need to compute a normal distribution with another mean vector, and in this case we are going to use the same covariance matrix. Okay, but you can compute one covariance for all the examples belonging to label 0. So you could have, for example, here a covariance 0 and here a covariance 1. So both parameters you can estimate it based on each of the labels, but in practice, if you compute only one covariance and you use it here, you can get very good results, and it is more practical because then you just need to estimate only one covariance matrix. So we can write the probability of our label in this way. So remember that y could be 0 and 1. If y equals 0, then this is 1, this factor is 1, and then we consider only this 1 minus the probability pi, okay, to 1 minus 0, so this will be only 1. And in the case when y equals 1, then 1 minus 1 will be 0, so we basically transform this into a factor 1, number 1, and here we will have pi to 1. So we will consider only the probability of getting the other label 1. So this is a compact way to represent the probability distribution of the label, where we know that there can be only 2 possibilities, 0 and 1. In the case of the conditional, given that y equals 0, we can simply write the Gaussian formula, specifying that each of the points that you will evaluate here will be a vector, and you will subtract the mean of 0, the mean 0, because we are talking about the label 0 here. Okay, here we have our only covariance matrix, and again here we see the mean vector for label 0, so this is when we're talking about dogs. In the same way, we will have a formula for the normal distribution, but now for all examples labeled as 1. So here we will have mu1 for all the mean vectors of the examples that are elephants, and the same mean here. So these are all the elements that we need to estimate. Now, how can we compute the parameters? So remember, now we are talking about generative models. We need to estimate some probability distributions that are these 3, and once we have computed this, we can apply the Bayes rule to make a new classification. And to be able to compute this probability, we need to know what this covariance matrix is, this sigma. We need to know what is the value of the mu0 and the value of the mu1. Those are all the parameters that we need for implementing this, and of course the phi parameter here. So again, here we need to apply maximum likelihood. Specifically, we need to maximize the log likelihood. And as we saw before,